Hello everyone. So again, welcome back to the latest lecture session. So a quick recap of what we have been up to, in during this course, let's say, because that's going to more or less lead into the relevant topic we are going to discuss today, right? So what have we been up to? As in, we looked at relevant risk assessments and relevant laws and so on, yes, and then we moved on to remediation, right? In the context of remediation, we looked at two aspects. What were they? As in, let us say this is your soil surface, let us say, and let us say this is your groundwater table. Again, typically there is going to be a gradient, but now we are assuming, I am assuming here that there is no gradient. So let us say when you have any particular spill here, let us say, right, depending upon the type of compound, let us say it can reach out to this particular groundwater depending upon if it is LNAPL or DNAPL, let us say, right. It can lead to contamination of the groundwater. So, groundwater is contaminated here, and obviously as groundwater is going to flow, let us say you are now going to have a plume, right, contaminated plume, right, and obviously as you can see in this region you are also going to have contaminated soil here, right. So, until now obviously we have looked at those cases when or initially we looked at those cases when groundwater was remediated. How do we go about remediating such scenarios or sites, and then we looked at aspects, let us say, that primarily involved what do we say, remediating contaminated soils, right. And obviously many of these techniques go hand in hand, right, in general, let us say, as you might have sensed by now. There is no particular case, let us say, when you, or rarely do we come across a case when you have just groundwater that is contaminated, or just the soil that is contaminated. Sometimes just the soil contamination, yes, without groundwater contamination, depending upon the extent of time that has passed since the release of the relevant contaminants, let us say, right. But as we look at this particular aspect of this generic diagram or figure that I have here, so what is another phase obviously that can be contaminated, let us say. As in, we can also have NaPl, right, this is the NaPl that acts as a source or reservoir. So, soil is contaminated, groundwater or NaPl itself can be present as, what do we say, a different phase, let us say, right. But what is another phase, let us say, that obviously that can be contaminated here. So, that is obviously in the Vado zone, or when you have relatively unsaturated zones, let us say. So, you have the Vado zone, let us say, and obviously here let us say you have porosity here, right, the soil is porous, right, and here you obviously are going to have gas, right, or air entrapped here. So, you are also going to have, what do we say, the relevant contamination of the gaseous phase. So, until now we have typically looked at soil or sediments and then groundwater, and obviously also we are going to now look at the contamination of this particular gaseous phase, let us say, or the air entrapped, right. And again, obviously not all contaminants, let us say, will lead to the particular contamination of this particular gaseous phase, let us say, or in the Vado zone, if I may call that, let us say, in this case, right. Why is that, let us say, right. For example, if I have a metal, let us say, right, let us say I will go with chromium 6, let us say, right. So, this is typically highly soluble, it is not hydrophobic, right, it is typically highly soluble. So, this contaminant obviously would want to stay in the aqueous phase or in the water, right. It would obviously not want to stay in the gaseous phase or typically not be adsorbed onto the soil now, right. So, obviously when you have such kinds of contaminants, you do not need to be concerned about, let us say, the contamination of this particular air entrapped in this particular zone, right. But obviously which kind of contaminants do we need to look at, right. So, typically hydrophobic compounds, let us say, they do not want to stay in the aqueous phase, and obviously they look for, let us say, the organic matter, as we looked at, let us say. Again, there are other aspects involved here about why or what is the driving force here, but we are not going into that in this course anyway, right. But again, so obviously some of these hydrophobic compounds are also volatile, let us say, right. Some, not all hydrophobic compounds are volatile. So, when I say volatile, what do I mean by that, let us say, as in it does not want to stay in the aqueous phase, let us say, right, it wants to stay in the gaseous phase. So, let us say initially I had take a compound of, let us say, vinyl chloride, let us say, right, and that is only in the water, let us say, right. This is a 1 liter container, assume that, and this water is contaminated with vinyl chloride, and I put it in a 2 liter container, and and this is 1 liter and this is also 1 liter here. So, let us say I let it reach equilibrium, as in vinyl chloride is very volatile. So, the equilibrium might be reached within a few what do we say, minutes, right. So, what is going to happen after some time is that, you know, all the, or not all, pardon me, almost all the vinyl chloride that was initially in the aqueous phase will change phase and go into the gaseous phase, right. Again, so here the compound volatilizes, right. So, again that is the case, or for these kinds of compounds, you know, we are obviously concerned with the relevant contamination of this particular gaseous phase or the Vadose zone, let us say, right. So, now we are going to look at, let us say, how do we, you know, address this particular case, let us say, right. So, by remediation, you know, probably not here, at least it is a gaseous phase, right. So, how do we go about it? So, what did we do when we had what do we say, a compound that was highly soluble, let us say? What did we do in that particular case or context, right? As in, when if you had just chromium, let us say, right, you can think of pumping the chromium out, right. You know, that is one aspect. I think we even looked at one particular example in Ghaziabad where they were looking at it along with, let us say, or in conjunction with, I think, bioremediation, right. So, again, you know, soluble, let us say, it wants to stay in the aqueous phase or in the water, so you pump out the water. So, similarly here, let us say, you know, if you have a compound that wants to stay only in the gaseous phase or mostly in the gaseous phase, what do? Well, again, you are going to extract the gas, right. It is not pumping out the gas, or you can call that too. So, you are going to extract the gas, right. So, the next aspect obviously that we are going to discuss is going to be soil vapor extraction, right. So, this is what we are going to look at. So, we are going to look at extracting the soil vapor. So, let us look at some of the relevant aspects. So, let us say this is my relevant surface here, let us say soil surface, and all this is the subsurface obviously. Let us say my groundwater is somewhere out here, let us say, and this particular zone, you know, the gas here is contaminated, let us say. So, what am I going to do? I am going to have a vacuum source, right, a vacuum source. Yes. So, I need to be able to pump the gas out, right. So, for that I can, there are two ways to go about it. You will either have a vacuum source, and then as you know the gas flows towards this particular vacuum source, pardon me, right, you are also going to have these extraction wells, right, and these extraction wells are going to remove your particular gas here, right. So, you are going to have extraction wells, right. So, sometimes you can double up and have both the vacuum source and the extraction wells in the same what do we say, setup, but I think depends upon the site and so on, right. So, obviously, you are going to have this particular setup, and what else can you do to make this system work better though, right. As you are drawing something out, let us say, you know, there is always going to be some resistance over time again, right. So, you will need to have, let us say, an injection well. I mean, if I can call that an injection well, let us say, right. And what is its role now? It is going to let, or you know, the air come in, let us say, right. So, you are drawing air towards this vacuum source or towards this extraction wells where you are extracting the gas. So, obviously, let us say you are going to have to supply air, and that comes through from the extraction wells, right. So, let us say if my contaminated zone is this one. So, once I remove this contaminated gas, I am going to again provide fresh or uncontaminated air, that is again going to come in contact with either the contaminant or any other relevant aspects there, and again the contaminant is going to change phase into the gaseous phase, and then I am going to remove that, right. So, again it is a cycle more or less. So, with respect to the injection wells, there are two cases obviously, as you can well logically deduce, they are either passive or active, right. So, passive and active, they are self-explanatory. Passive, okay, let us talk about active in the first case. So, active, I am going to pump air in, let us say, I am going to pump air in. Passive, let us say, you know, it is open to the atmosphere, and again depending on the design, let us say it is going to be able to draw air in, pardon me, right. So, again active and passive here, right. So, in this context, what else do you need to do, let us say, to be able to remediate this particular what do we say system, let us say, right. You also need to have an impervious layer here at the top, let us say, right. Again, two aspects. First, when you notice that this particular vadose zone or the gas there is contaminated, you obviously do not want that particular contamination to escape out, you want to control that, right. And once you start pumping your relevant what do we say contaminated gas out, again you do not want to have great level of interference from the outside what do we say environment too. So, you again need to have an impervious layer here, right, impervious layer, right. So, what are the major aspects that obviously are required? You need a vacuum source, you need an extraction well, right, and obviously you need an injection well, and what else do we have? Again the impervious layer, right. Again in the context of injection wells, we have either the active or the passive wells, right. So, this is more or less the what do we say summary, if I can say, of relevant system, right. In what way can this also aid other what do we say systems now, right. And I think in the context of maybe bioremediation, let us say we did look at this briefly, but how does this again help bioremediation, let us say, right. So, this aspect is that if you have other contaminants, let us say, right, or if some of these compounds, let us say, that are relatively soluble or reduced compounds, what do you need? You need an electron acceptor. Typical electron acceptor, it is oxygen, let us say, but beneath the subsurface or beneath the in the subsurface, typically oxygen levels are relatively low, right. So, while you carry out this soil vapor extraction, what do you see happening here? You obviously see that you are introducing, let us say, air into the system now, right, or obviously I am also introducing oxygen into the system. So, this oxygen based upon where you are pumping this what do we say air in, either into the aquifer or let us say just at the what do we say top of this particular aquifer. If it is above the top, you will have some what do we say oxygen transfer into the water, right, based on again what do we say phase change, let us say, right. You want to have equilibrium between oxygen in this particular vadose zone and oxygen in the groundwater table, you will have that. Or if you pump what do we say air into this particular aquifer itself directly, you are going to have greater oxygen concentrations in this particular aquifer, and that can aid your remediation process because it can further bioremediation or it can enhance bioremediation, especially when the compounds are reduced and you want an electron acceptor, right. So, that is one particular case. Again, soil vapor extraction typically has been seen that you tend to increase the or enhance the effects of natural attenuation, let us say, right. So, that is one aspect to keep in mind. So, let us look at some of the advantages of this particular system. So, the major advantage obviously is that you are not introducing any reagents here, right. So, no reagents, as in no chemicals, right, nothing out there, right. So, you do not need to be concerned with what do we say adding any involuntarily adding contamination or any contaminant or residual contamination, as in with respect to soil washing we had to put in surfactant. So, even after you pump out all the surfactant, obviously you are going to have some residual surfactant, again that can cause issues. But with what do we say soil vapor extraction, obviously that is not going to be the case, that is one remarkably good advantage out there. But what is the disadvantage, let us say, right. What is the disadvantage we face? As you could have sense, you need to have, or the system needs to be such that, or the site needs to be such that you are going to, or that it is going to allow air to flow through, right. So, it needs to be relatively permeable, right. Site needs to be relatively permeable, right. So, that is one key aspect, the practical aspect that can affect the relevant efficiency of your particular system here, right. So, that is something to keep in mind, right. So, now let us move on and look at obviously the relevant balance, right. Again we are going to look at the case when equilibrium has been reached. So, typically what do you have, let us say we have total mass or m at time equal to 0 is equal to mass in the aqueous phase plus mass in the soil plus mass in the NaPl phase, right. And now let us say with soil vapor extraction, you are obviously also going to have, or pardon me, even without soil vapor extraction, in this case of a volatile compound, you are also going to have the relevant compound present in the gaseous phase, let us say, right. So, let us just write down these terms here. So, let us say here, unlike earlier, I am going to define the total porosity as porosity of what do we say in terms of water, gas, and that occupied by the NaPl, right. So, it is slightly different. Earlier we more or less took this particular case as, how did we understand this? S times porosity here, right. That is how we looked at it, and for water we more or less considered it to be 1 minus S times porosity. So, but because we have another term here, we are going to look at total porosity, let us say, and I am going to say the 3 fractions are occupied by water, gas and the NaPl. So, let me take that down here. So, I need the volume of what do we say, water. So, that is porosity of what do we say. So, that is going to be the volume occupied by water, right, times the concentration in the water, right. So, C is the concentration in the water plus mass adsorbed onto the soil, right. So, how do I get that? As we know, volume bulk density of the relevant soil into Q, and what is Q? By now we should be able to understand this. This is the mass of contaminant per mass of soil, let us say, right. So, more or less the concentration adsorbed onto the relevant soil, let us say, right. So, again as you know, soil and contaminant in the water, let us say you are going to have an equilibrium, right. So, Q is going to be in equilibrium with C. C is the concentration of the contaminant in the water, and typically we have looked at or assumed that it is a linear relationship, and it is what do we say, explained by the partitioning coefficient, right. So, that is something we have looked at. So, again we can come back to that, and NaPl, I think we again have this, the density of NaPl, right, again the volume occupied by NaPl, right, into the mole fraction, right. So, into the mole fraction. Obviously, if it is a pure what do we say, NaPl, the mole fraction is going to be equal to 1, right. So, I think that is something that we looked at, and now that we have gaseous phase, let us say, what do you have here? So, again we have the concentration of the relevant gas, let us say, or concentration of the total, not concentration, pardon me, the total volume or fraction of this particular total volume is occupied by gas. So, that is what we need here. So, I am going to multiply the total volume by the porosity that is occupied by gas, let us say, or the gaseous phase, times concentration in the gaseous phase, right. So, these are the terms that we have. So, we will look at 2 or 3 cases, because these are what you would come across out there. So, let us say in the first case, I will just look at the case when there is no NaPl present, let us say, right. There is no NaPl present, right. So, this total mass, let us say, is nothing but, let us just write down terms that we have here. So, volume occupied by water times concentration of the relevant contaminant in the water plus volume, right, bulk density, and Q. Q, as we know from here, is in equilibrium with the concentration of the contaminant in the water, right, and now I am assuming there is no NaPl. So, I am going to have these terms here, right. So, rho GV, which is volume of gas times concentration of gas, let us say. But again we want to obviously be able to express the relevant terms in terms of the variables that we are used to, let us say, and what is that? Typically we are looking at or expressing them in terms of the concentration of the contaminant in the water or the aqueous phase. So, let us just look at how to express this concentration of the gas in terms of concentration in the of the contaminant in the water. So, as we looked at earlier, let us say in the example that we looked at briefly, vinyl chloride. So, let us say if I let it equilibrate between the water and the gaseous phase. So, this is the gaseous phase and this is, let us say, the aqueous phase or the water here. What do you observe? The vinyl chloride, let us say, even though it is highly volatile and most of it, let us say, is present in the gas, you will still have some vinyl chloride present in the, let us say, which I am going to represent by this, that is going to be present in your particular water too, right. So, again there is going to be an equilibrium between the gaseous phase and the aqueous phase, right. And what is the relationship that we typically have that gives us this particular relationship? So, that is typically the Henry's law, and from there we end up getting the Henry's constant for different what do we say, compounds. So, again Henry's constant has different units. So, depending upon the relevant units of Henry's constant, it can even be dimensionless, it can be pressure per mole, right, or it can even be what we say, concentration of water by gas, but typically let us say it is pressure, partial pressure of that particular gas by the concentration of the contaminant in that particular water, let us say, or in the aqueous phase. Or Henry's constant, depending upon the units, is also concentration in the gaseous phase by concentration in the water, let us say, right. So, that is what we have here. So, for now we are going to use this particular nomenclature now, right. So, let us see how I can plug this in. So, obviously here I need to, I am looking for expressing concentration of the gas in terms of concentration of the water, right. So, here as I can see it is nothing but Henry's constant times concentration of water, because I expressed it as C, I am going to leave that as C now, right. So, I take this particular term out, right, as when I am going to take V C out of this particular set of variables, and now I am going to simplify that. So, porosity of occupied by water, let us say rho B K P plus gas and Henry's constant. Again Henry's constant, as I mentioned, has different units. So, you need to look at the kind of units you have, or you need to if you are looking for a ratio of concentration of gas to concentration of water, depending on those units, you need to look for the relevant Henry's constant. And for most compounds out there, or almost all, we will have the relevant Henry's constant for at different temperatures and so on, right. So, again we have this out here, and this is what we typically have, right. But one aspect to keep in mind, as in we similar to the vinyl chloride case that we just looked at, as in here we looked at the vinyl chloride case, right. And what do we observe here, let us say, right, that if it is a volatile compound, typically let us say most of the concentration will be present in the gaseous phase. So, rather than expressing this particular set of variables in terms of concentration of water, it is better to express it actually in terms of concentration of the gas here. So, I can express this as V times concentration of gas by the Henry's constant, right, times porosity of water, so rho B K P plus rho G times H, right. So, this is what I end up with. If I take the Henry's constant inside this particular set of variables, I end up with something like this, right. So, again how else can I simplify this further? So, M total by V, the total mass, M total is the total mass by the total volume. So, that will be the total concentration. So, that just gives us an idea, let us say, right. Obviously that the concentration is spread over, or the contaminant is in 3 phases: water, soil and in the gaseous phase, but total concentration sometimes just gives you an idea of the relevant system, right, is obviously nothing but concentration. I took this volume out to the left hand side, concentration of the gas, right, by Henry's constant, rho B K P by Henry's constant plus porosity of this particular occupied by this gas. So, this is one particular case that that one set of equation that we typically use widely anyway, right. So, now until now we have looked at the case when no NaPl was present, right. And again why do we need such particular cases or systems now, right. Again, what is the reasoning behind having to analyze for it, or break it down in these terms? Because let us say a site is contaminated and you want to deploy your relevant resources, time and manpower, right. And what do? You need to look at or prioritize which aspect to look at, let us say, right. So, obviously you will need to see which particular phase has the greater what do we say, fraction of the contaminant in it. So, for that obviously I need to be able to come up with these theoretical calculations to know which particular phase is it that I am going to prioritize and then address or try to address, let us say, right. So, in those cases let us say to understand the system and analyze the system, you are going to have to do or conduct such analysis. So, now we will also look at the case, a very generic case when NaPl is present, let us say, right. So, NaPl is present, let us see. So, let us just write down the case that we had earlier. So, total mass is equal to what did we have here? So, I think we had epsilon or porosity of water times volume and concentration of water, right. And again we have V rho B Q, Q is nothing but Kp times C, this is the mass in the relevant adsorbed onto the relevant soil. So, in the gaseous phase, so this is the volume of the gas times the concentration in the gas, right. So, concentration in the gas and divided by concentration in the water, Henry's constant, right. This is something that we have. So, if I can write it, okay, I will write it as concentration in the gas for now, and then again what do we say, porosity occupied by this NaPl, right, times the volume and density of NaPl, right, into the mass fraction, let us say mass fraction of that NaPl, right. So, that is another aspect obviously to keep in mind when we have what do we say, the relevant aspects with respect to the NaPl2. But in this case what is one aspect that you need to keep in mind? If the NaPl is present, NaPl let us say, or even if I say it is, or if I consider it to be a pure NaPl, let us say, what is going to happen? You have the pure NaPl present, and that is going to be in equilibrium with your water. Let's say if the equilibrium has been reached, maybe because enough time hasn't passed, what do we say, the system has not reached equilibrium, maybe it's relatively far from equilibrium, but let's say we are going to look at the case when there is an equilibrium between the NaPl and the relevant water, let's say. So then what is the C going to be, right? So that would be the solubility, let's see, solubility of that particular compound if the relevant equilibrium has been reached, right? But if the equilibrium has not been reached, right, it will typically be less than the solubility, right, as in there is only a particular threshold or maximum concentration that water can hold with respect to any particular ion or compound, let's say, right. So if the equilibrium has been reached and you have the pure NaPl, so if you have the pure NaPl and groundwater, right, in contact, if equilibrium has been reached, the concentration here of that compound will be the solubility rate. But typically, let's say maybe not enough time has been reached, or for the relevant contaminant to diffuse to all this particular region out here, that takes time, let's say. So let's say your particular concentration in the water has not yet reached the solubility levels. So I can say that this concentration is going to be equal to a fraction of this particular solubility, let's say, right. So solubility is the maximum that can be, but let's say if equilibrium has been reached or it's relatively nearer equilibrium, though I can say it's some fraction of the solubility, right. That's how we are going to express it as, right. This is that fraction x, let's say, plus V rho B Kp times x times C of solubility, plus again rho gas V, Cg is nothing but Henry's constant into concentration of water. Concentration of water, we are expressing it in terms of solubility. So right, this x times C solubility plus obviously again the mass in NaPl, volume, density of NaPl and mole fraction of this NaPl. Again keep in mind this x is different from here. Again what is this x? Let us say what are we trying to use that to represent, as in the concentration, there is particular concentration of the contaminant in the relevant aqueous phase, but let us say even though the NaPl is in contact with your water, let us say equilibrium has not yet been reached, right. We want to obviously express it in terms of concentration of solubility to be able to understand the system better, and in that case I am just using this expression as concentration, actual concentration in the water or in the aqueous phase is x times the concentration or the solubility, let us say, right. So that is how we express that as, and you can analyze the system from this particular point of view, I guess, right. So now I guess we are almost out of time, so we will look at the or talk very briefly about the design and go ahead from that, let us see, right. So let us say you want to design this particular system, the remediation system, let us see, right. So obviously what do you need, or think of what we did in the pump and treat, let us see. What did we do in the pump and treat now, right? In that case, if you remember, let us say if this is the top view, let us say if this is the top view, and let us say I have my contaminated plume like this, right, and I can place one particular well here, right, based on the Avendel et al. Design, and depending on the flow rate, let us say I can capture this particular flow path, right. That is something that we looked at, right. This is the boundary of the flow path that can be captured and so on. So what were the key aspects there, as in we need to figure out, or we had to figure out how many extraction wells to have, what is the rate of extraction that we needed to have, and what is the placement of this particular extraction well, right. The placement here, that is something that we had to look at, right. So similarly again what are we going to look at? We are going to look at placement, let us say, right. So for the placement, let us say what are you going to look at, let us say, right. You are obviously going to have to understand, let us say, or you need to consider, let us say, those particular areas where the vacuum is still, what do we say, above certain threshold values, as in if this is my surface and I am applying vacuum here, let us say. So there is going to be a pressure drop, but the further I move away from this particular vacuum source, the pressure drop is going to decrease, right. So let us say if I am pumping air out from here, or I am introducing a vacuum source here, as I move away from this particular source, obviously the effect is going to be relatively less. So based upon which particular source or type of what do we say literature you look at, there are different ways to calculate what the radius of influence, if I may call that, right. So you are going to have to calculate that radius of influence, let us say, and then look at relevant placement and so on and so forth, right. Obviously, one aspect is that you also need to have monitoring wells, right. You obviously need to have monitoring wells other than just your extraction wells and so on, right. Yes. So, again just a quick recap before we close the or end the session for today. So, we are going to have your what do we say now, your vacuum source, extraction wells, impermeable layer cap, right, and also injection wells, active or passive, right, and if required you will also have multiple monitoring wells, right. And obviously, there are other aspects to be looked at, as in when you pump it out you need to look for or consider the off gas treatment or treatment of this particular gas, and also depending upon the system, if you are also pumping water out, you will also need to look at separating the water and gas and then treating both the water and the gas, right. So, depending upon how you set up your system, you might end up pumping out, let us say, both the or extracting both water and gas, right, and let us say, or you will have some water entrapped too, depending upon the depth at which you are looking at, let us say, and let us say then you are going to have to look at separating the water and gas and then treating both these phases, right. So, again these are different aspects to be involved, but we will look at the design and maybe an example again in the next session, and that is it from me for today, and thank you.